All right, so assignment 7.4. In number 1, write out the power series for each one of these. And so we need to keep in mind that we're looking at 1 minus, or A1, I should say, over 1 minus R. And that when I look at the power series at the beginning of the lesson, that if I go 1 over 1 minus x, it equals 1 plus x squared plus x cubed, and so on. So I can use this pattern and understand, all right, 1 subtract 3x. I'm just going to follow this pattern, but instead of x, I put in 3x. And you have it. If I write this in sum notation, we have the first term, we have the common ratio to the exponent n, and the interval of convergence, you would take 3x between -1 and +1 when you divide by 3 to get x by itself. That's what's called the interval of convergence. So when x is between -1/3 and 1/3, that's when it converges. Number 2. So 2 over 1 minus x cubed. So we can write this from 0 to infinity. 2 is the first term. X cubed is the common ratio to the exponent n. And if I expand it a bit, following this pattern, it's 2 is the first term. And then plug in plug in 1, and you get 2x cubed. Plug in 2, and you get 3 times 2, that's x to the 6th. Plug in 3, and you see the pattern. The interval of convergence, again, you take the common ratio between -1 and 1. Now, this one you'd cube root it, and so if you cube root it, the cube root of -1 stays -1, and the cube root of 1 stays 1. And that's called the IOC, the interval of convergence. Number 3. So the first term, the common ratio, is going to be -x. So think of this as 1 minus -x. So it has to be in the form 1 subtract the common ratio. For these to match, it needs to be -x. So when you expand it, it's the same. So it's -x to the n. If you plug in 0, it's x. If you plug in 1, it's -x squared. If you plug in 2, it's +x cubed. It alternates. You can see the pattern. The interval convergence, I take -x between -1 and 1, divide by -1, it's going to stay the same. When I divide by -1, the arrows change and the signs change from negative to +1 and positive to negative, but ultimately this is the same as this. Number 4. So it needs to be in the form of 1 subtract. So I'm going to write it, instead of this, subtract. They're the same, right? But this isn't the right form. So it goes from 0 to infinity. The first term, and then x plus 3 to the n. And if I multiply it out, if you plug in 0, if you plug in 1, if you plug in 2, and so on. Take that interval, the common ratio between -1 and +1, subtract 3, and there you go. For it to converge, it must be between -4 and -2. Number 5. Three over 4x we're going to write as 1 minus 4x. So 1 take away 1 is 0, and a negative times a negative makes it 4x. They're the same, but it's in the form 1 subtract now. That's what the series is going to look like. So the first term, and then the common ratio to the n. If I plug in 0, if I plug in 1, if I plug in 2, and then you get the idea. We're going to take the common ratio between -1 and +1, and then solve for x. We'll subtract 1. Oops. Subtract 1 and then divide by -4. And then you can change the arrows around the other way if you want to. And that's called the interval of convergence. Number 6. So again, it needs to be in the form 1 subtract. So 1 subtract what would be 2. And then 2x. So it's -1 and 2x. So when you plug in 0, it's 1. Then it's -1 plus 2x. -1 plus 2x squared, and so on. Oh, what am I forgetting? So add 1, and then divide by 2. So it's between 0 and 1. Number 7. If Find a function for each of the following geometric power series. Also give the interval of convergence. So when I look at number 7, I'm trying to figure out the pattern in terms of what to follow here. So it's geometric. I'm thinking of a1 over 1 minus r. So when I plug in 0, the answer is 1. And then the common ratio is 2x, so it's 1 minus 2x. And then I take 2x, and then to find the interval of convergence, put it between -1 and 1, divide by 2, and then you have the interval of convergence, and you have a function that matches it. Number 8. Kind of working backwards. So if I plug in 0, I get the answer 1. What am I multiplying by every time is -1/2 times x. So it's 1 subtract -1/2 times x. That's what I'm multiplying every time. And then the -1/2 x put between -1 and 1. I'm going to multiply by -2. We can also write it this way. Usually the smaller numbers on the left and the bigger numbers on the right. That's called the interval of convergence. Number 9. So again, if I plug in 0, this time the answer is 4. 1 subtract, the common ratio is x minus 1. And then take x minus 1 between -1 and 1. Add 1. And you have the interval of convergence. Number 10. So don't assume, plug in 1 and you get x squared. And then 1 subtract the common ratio. And then x squared between -1 and 1, square root. And you still get this answer. And it's really the absolute value of x squared. It has to be less than 1. So between -1 and +1 would answer that. Number 11. So plug in 0. Anything to the 0 is 1. And then 1 subtract sine x. To undo this, you have to do inverse sine. So inverse sine of -1, that's at the bottom of the unit circle or the top of the unit circle. It's between -π/2 and +π/2. All right, number 12. Use the results of example 7 on the previous page to write a power series for f at x equals e to the x squared. Show for 4 terms and the general term. So on the previous page, e to the x was the same as, where is it? E to the x was the same as this. So that's what I'm going to follow. 1 plus, and then I plug in x squared. I plug in x squared. I plug in x squared. And that pattern continues. What would the general term look like? So if you plug in 0 factorial, by the way, is 1. If you plug in 2, or plug in 1, then 2, then 3, and you can see that it matches. That's because you take and you multiply these together. That's why it's 2 times n. 13. So again, I'm going to take the result that we did with e to the x and just multiply it by x. So I take this result and just multiply it by x. So x times 1, x times x, x times x squared over 2 factorial, x times x cubed over 3 factorial, and so on. And then what would this be as a general term? So if I plug in, it would be n plus 1 over n factorial. So if I plug in 3, it's 1 plus 3, which is 4, right? You have to add 1 every time. That's what the x does. It has an exponent of 1, and it adds 1 to whatever the exponent is. 14. Find a geometric power series and then show 4 terms in the general term. So this is the same as this. And then with negative x, we use what we did at the beginning, which is 1 plus negative x squared plus negative x cubed plus da, da, da. And that's what it looks like. What's the general term look like? It's alternating. So it needs a negative 1 to the n, and then it's just x to the n. Number 15. Use the answer in problem to find the power series for 1 over 1 plus x squared. So same thing, 1 plus, this is really 1 subtract negative x squared. So we need negative x squared, so instead we just put in negative x squared. And then the general term again, it's alternating. Oh, does it ask you for the general term? No. So there it is right there. Use integration to find a power series for arctangent. So recall that this is the rule for arctangent, 1 over 1 plus x squared. If I integrate it, it goes back. So the derivative of arctangent is this, and if I integrate it, it goes back to this. So if I think of the power series, like what we just did, I'm going to simplify it. And then integrate this. So the integration of 1 is x, and then you add 1 to the exponent and divide. You add 1 to the exponent and divide, and then there's the pattern. Oops. That's what arctangent equals as a series. $17. Use this to find the following and use sigma notation. So if that's what f at x equals, then f at negative x it would be negative x to the n over n. The derivative n times 1 over n means they cross out. That's what the derivative would look like. Number 19, what would it look like if you integrated it? So I got to add 1 to the exponent and then divide by n plus 1. And I'm integrating from 0 to 1. If I plug in 0, I'm not going to write that as a limit, am I? I'm going to leave it go. That would be a 2 on the bottom. All right, number 20. All right, I'm going to take a break there. So, at number 20, I'm going to continue the next video there, and it'll be 20 to the end. All right, Mr. G Math over and out. Awesome job doing your work with me. I know this isn't easy. Till next time.